Hello everyone, my name is Nikola Tunguz, and I'll be presenting you a paper on the segmentation of electroencephalography data in eye tracking applications. So, a brief overview. We'll first be introducing the topic in the background, and then we'll be talking about a literature review of the paper, followed by the actual technical details of the paper's approach, followed by the results, and a general conclusion. So, to begin with, the paper's topic is segmenting electroencephalography data. These EEG data are just measurements of electrical activity in the brain. This data can provide insight into overall human cognition and health, as well as behavioral patterns. The problem with this is EEG data is strongly affected by noise. This can be anything such as stray thoughts or body movements that happen during data collection. And the paper provides a new way to isolate ocular events from this data. These ocular events include blinks, stations, and speeds, just rapid eye movements. The background to the paper is that the work was based on over 50 other previous works, and there were only a few of them that were very significant. The first being end-to-end object detection with transformers. This work created a new framework known as DETR, which created a new approach to object detection that used transformer architectures. These were previously only used for language processing, but in this architecture, they were used to create bounding boxes directly. Another work is a fully convolutional network for time series segmentation applied to sleep staging. Generally, this work essentially just created a new model that used time series segmentation to identify sleep stage electroencephalography. And the third major work was using deep learning to classify saccade direction from brain activity. Essentially, this work just collected EEG data and metric information and processed them efficiently. So, the paper itself suggests a method to identify and differentiate molecular events from EEG data. It suggests that object detection from DETR can be adapted using time series segmentation, and by combining them, a new architecture, DETR time, is created. Now you may be wondering, what is time series segmentation? Well, it's the partitioning of continuous data into smaller time segments. Aims to split continuous blocks of classification labels and isolate them from the rest of the data. Overall model architecture of DETR time was a convolutional backbone that directly took in the EEG data. It was then passed into a transformer that resulted in ocular events. Then object detection was used to predict what events occurred when. And what the data output would look like is something like this. As you can see on the top, you have the classification labels of the saccade, fixation, and blink. At the bottom, you can see time as they were segmented. So the EEG data itself came from four different types of events: reading and movie watching, which I'm sure you're all aware of, as well as large grid, which you can see in the bottom left, where participants were asked to find a number and had to search for it in the grid. Similarly, with visual simple search, participants were given a specific symbol and needed to find it in a group of larger symbols. Overall, the DETR time performance was significantly better than any other model previously. Across all event times, DETR time was, on average, better. Free to pause the video and read this table on your own if you would like. In bold at the bottom, you can see the DETR time averages for each data collection. The overall results of this paper were that the DETR time model outperformed most other models in molecular event segmentation. However, within the relatively small experiment, some participants did not have their data analyzed. This means the model was too specific. The overall significance of this work was resulting in a high ability to identify ocular events, and it opens the door to further research in greater EEG analysis, where it can be used for greater purposes, such as detecting dementia in patients. In conclusion, Leader Time provided a new overall solution to segmenting EEG data. By using time series segmentation, performance significantly increased across all ocular events. This research provides groundwork for more future work, specifically in using time series segmentation in greater scopes and in non-traditional ways. And similar with ocular event connection with EEG, actually processing ocular processing EEG data with greater human behavioral patterns. Here are the references for this work. If you have any questions, please feel free to email me at this email address. Thank you for watching. Have a wonderful day.